Let's now talk about this problem concerning the t-test. The data shows the width to length ratios of beaded rectangles. Doesn't it appear that this data follows the golden ratio, which was an aesthetic standard in Western Europe, for example in the Mona Lisa, in the architecture of the Cathedral of Notre Dame, and other places. So for this one, the null hypothesis will be that the average of these ratios is indeed equal to the famous golden ratio, which works out to be square root of 5 minus 1 over 2. And for the purposes of this problem, we'll use the 3-digit decimal approximation of 0.618. So that's the golden ratio from classical Western European art and architecture. The alternative hypothesis. For this one, I'm certainly no expert on the artistic standards of this particular people group of Native Americans. And so I don't have a feel as to whether or not it should be less than or greater than, and so I will be very modest and simply say that the alternative hypothesis is that mu is not equal to 0.618. Notice again, just like with the z-test, that this decision got made before computing the average of the data. Okay, we took alpha to be 0.05 as usual, unless the problem says otherwise. Okay, now we compute the average, and the average of these numbers works out to be 0.661, and the standard deviation of these numbers works out to be 0.0925. So now we compute the t-value, which will be equal to x bar minus mu divided by s over the square root of n. Okay, so x bar we worked out to be 0.661. I'm going to get a couple more places there. So 0.661 minus 0.618 divided by the value of s, which was 0.0925, divided by the square root of 20. So the value of t will be equal to 0.661 minus 0.618 divided by 0.092511 over the square root of 20. So that works out to be 2.054. Now, once again, we need to figure out if to retain or reject the null hypothesis. To do that, there are two ways to do it. First way is by looking at the p-value. So in this case, we have a cutoff at, or the test statistic is at 2.054523. And so I need the area to the right as well as the symmetric area to the left. And so the combination, the combined area, would be the p-value. Okay, now how do I get that? Whoops, let me go one bit. Okay, so in Excel 2010, the command will be t.dist. Now notice there are three choices on t.dist. The without any extra typing, which turns the left-tailed. Then there's also an option for getting the right-tailed, but the one that I want is this one for a two-tailed. So t.dist.2t of this number, with in this case 19 degrees of freedom, because the number of degrees of freedom is n-1. So in Excel 2010, the command is this, 0.053941. In Excel 2007, the command is tdist. There's no t dot options available in 2007. And then I have disk number 19 and then 2 tails. So you notice the third option is the number of tails that are permitted. In my case, I want 2 tails. Okay, also the first number here, H3, must be positive. That's positive 2.054, so that's good. And I get the same answer back, 0.053941. So there's our p-value, is this combined area, 0.0539. That's bigger than alpha, and so the decision will be to retain the null hypothesis. The second way that this problem could be done is by looking at the critical values. So let me lift this up to the top. The second way that this problem could be done is by looking at the critical value. So once again, I have the t-distribution with 19 degrees of freedom, and we need to figure out the mark so that the total area that I've shaded here is equal to 5%. Okay, so in Excel 2010, the command is t.inv.2t. The probability in my case is 5% and 19 degrees of freedom. And so when I hit enter, I get the critical value of 2.09. Now, you don't have to do what I'm about to do. Another way of getting this would be t.inv of 0.02519, which is another way of stating that 2.5% of the area lies in the left tail, and I get the same answer as well, negative 2.093. Another way of doing this problem would be t.inv of 0.97519, stating that 97.5% of the area lies to the left, and that returns positive 2.093. So just to show you the interconnectedness between the commands, t.inv 0.0519 gives, what I typed wrong, t.inv.2t of 0.0519 gives the area 2.093. Now in Excel 2007, there's only tinv, the one command, and the area is the two-tailed area. In my case, I have a two-tailed test, so I put in 0.05 without any modifications, 19, and that is the two-tailed area, 2.093. Okay, so that is 2.093. And in a little bit, I'll talk about how to do this on the calculator. So the other extreme on this side, of course, would be negative 2.093. And so on this extreme, the decision would be to reject the null hypothesis. Also on this extreme, the decision is to reject the null hypothesis. But in between, the decision would be to retain the null hypothesis, to fail to reject. Now in our case, 2.054 falls about here, barely inside this range, so the decision is to retain the null hypothesis. And so we retain the null hypothesis. We do not have enough information to conclude that the golden ratio was not an aesthetic standard for the Shoshones. Now notice the funny way that this is written. If we have a double negative, we do not have enough information to conclude that it was not an aesthetic standard. It's not written in the more plain English that you'd learn in English class. We have enough information to conclude that it was an aesthetic standard. But by removing the double negative, you get a statement that is far too definitive. And so I don't want to say that, because there's always the possibility that with more information, we may later choose to reject the null hypothesis. Just right now, we cannot reject the null hypothesis. Okay, before concluding, let me talk about the TI calculator. So suppose we have the problem is to figure out the area in both tails. Now to figure out the area in one tail, it's second distribution, TCDF, and then negative 10 to the 99, comma, negative 2.054523, comma, 19. So this would find the area in the left tail, negative 10 to the 99 to negative 2.054523. Then to get the area in both tails, I just simply take that and multiply by 2. And so this should give me the same answer that I had before, 0.053941, which is exactly what we got in Excel. As noted in another video, in the TI 83 and 83 Plus, it is not possible to figure out the critical values for the T distribution. However, it is possible on the 84 and up, apparently. I don't have that on the video here. In another video, we talk about how to figure out the critical values using the table found in the back of the textbook.